This section is called velocity and other rates. Whatever function you come up with here, if this is the amount of money that a company has over time, so we'll do something else other than, it's easiest to think of time on the bottom, but so if we change it to dollars over time, some company, this is how much money they have, I don't know, in their bank account or whatever, or their total value, or like the value of their the company. If it goes up and then it goes down, it goes up here and goes like that or whatever, right? Any given value here is a certain number of dollars, right? This is $2 million up here and this is $1 million here or whatever. If you say, this point here, well, it's worth 2 million at that point. If you look at the slope of that graph, what would the units be on the slope, and what would it be telling you? It would be dollars per whatever this is measured in. Yeah, like if this is year or month or something like that, whatever this function is, it would be in dollars per year, and it would be telling you the rate of change of whatever this quantity is. If this is the value of the company, then the derivative tells you the rate of change of the value of the company. It's the rate of change of whatever you're looking at. If you're looking at value of company, derivative is rate of change of value of the company, and the units on the rate of change come from whatever you're looking at, dollars per year, right? It's going to tell you at this point it's going down, meaning exactly what you think it means. What does it mean? Value of the company is, it's decreasing, so it's got a negative derivative there, right? Whereas then you turn around here, now it's got a positive derivative. All it's saying is value of the company is going up, right? It's exactly what you know the slope is. The derivative is the slope. So if you talk about at this given instant right here, value of the company is increasing. Okay? At this given instant, this is worth knowing here, what's happening with the value of the company just for that instant? It's not changing, right? The rate of change at that given instant is 0. That's actually how you're going to use derivatives to find maximum and minimum points. If you want to find maximum and minimum points, how can you use a derivative to find them? Find where it's 0, like find an expression for the derivative and then make an equation where that's equal to 0. So that's going to be a concept you use in here. The other things here, if the derivative is positive, in other words, if the velocity is positive, then the object is moving which way? Yeah, positive or forward or whatever you're calling it. Forward, up, right, whatever, I don't know. Positive direction, depending on the context, right? If the velocity is less than 0, then just the opposite of that, right? Moving backwards, down, whatever in your situation is the negative direction. Left, negative direction. If the derivative is 0, then what's happening with the object? It's stationary, not moving. If you look at the derivative of velocity, you have to think about what that is, right? The rate of change of velocity is how's the velocity changing. So if you know that this is acceleration, right? When acceleration is positive, what's happening with the object? I mean, basically the best way to describe this is if the derivative of velocity is greater than 0, velocity is increasing. I know that in everyday language sometimes we talk about acceleration and deceleration. Physicists, as far as I have experienced, don't tend to like to use the word deceleration. Instead, they just talk about positive or negative acceleration. Because if you talk about acceleration and deceleration, and then you also talk about positives and negatives, like if you have negative deceleration, what does that mean, right? Does it actually mean acceleration? So it's probably safer to just say positive acceleration and negative acceleration. Remember that we can have negative velocities here. So the term slowing down, speeding up, speed here isn't dependent on the direction, right? So if you're already going negative 100 kilometers an hour, you're going backwards, right? If we're talking about velocity, and you have a negative acceleration, what's going to happen with your speed? What's happening with this? Getting less or more? It's actually going to go like this, right? If you have negative acceleration, it's going to become 200. So the terms speeding up and slowing down are probably you run into troubles. It's better just to say is your velocity. I mean, this is the rate of change of velocity. That's what the derivative is. So if it's positive, velocity is increasing. Just like value of the company, right? You have this thing. Its derivative is positive, value is going up. Its derivative is negative, value is going down. Put it in that context. If this is like this, what is happening? Is it not moving? This is the one that sort of tricks people sometimes. What's happening? Is it? Yeah, it's constant velocity. Whatever it's doing, it's continuing to do that. All right. Really, there's no other new concepts here. Other than things like what I mentioned before, if you have a projectile, I know that in physics, how do you find the maximum height of a projectile in physics? So what do you do? Well, I mean, if you're only talking about parabolas, I don't know if you do this, but you kind of just look at halfway in between those 2 points, right? Gravity acceleration is constant. Anyways, if it's a quadratic, it's symmetric, right? So if you knew when it's there and when it's there, you could actually find this point just by doing that. We're going to extend this a little bit more and be able to use calculus, like what we said there. If you want to find it's a maximum or minimum, you look where the derivative is 0. Okay? Max or minimum. Distance or height or position. Distance, height, position, whatever you're calling it, can be found by doing what? By setting velocity, in other words, the derivative, equal to 0. Right? If you wanted to do the same thing for acceleration, the relationship between velocity and acceleration, it's the same thing, right? If you wanted to know when it is at a constant velocity, you could set acceleration equal to 0. Looking for that horizontal tangent is an important concept, right? If you want to know when the thing's at rest, you want to know when velocity is equal to 0. Or in other words, you want to know when s prime is equal to 0. So just write an expression for the derivative. If you're given the original function, write an expression for the derivative and say equals 0, and you get an equation you can solve. This is taking it farther than you have in calculus, because we can now talk about completely imaginary situations like this, right? In physics, you have to talk about the real world. In math, you can talk about imaginary stuff sometimes, and you can say, if you're trying to come up with a nice question to give your calculus class or something like that, you could try and look for a nice real world example, or if you wanted to give them a cubic, you can just say a particle is moving according to this function, because then it can be anything, right? It doesn't have to be a real thing. Particles can move however you want, right? They can go like this. It can be anything. So if this is the position, even if you don't have any physics formulas or anything, you can create your own physics formulas by using the relationship between those things. Velocity is the derivative of position. Acceleration is the derivative of velocity. And then use the concept of, if you want to know when it's at rest, find where velocity is 0. I would start, as you work through this, I want you to work through some of these things and say, write out a statement first to say, if I want to know when it's moving to the right, I want to know when its velocity is greater than 0, right? When is it greater than 0? To find where it's greater than 0, you have to first know where it's equal to 0, which you did in the previous question, and then you can decide. Drawing a diagram, I was just thinking I'll do something like it's moving forward to this much, and then it's moving and this kind of thing. I wasn't thinking of anything more sophisticated than that. There's lots of questions here for you to think about. It's better if you work on some of these and then we discuss any problems rather than taking hours and hours to work through all of them. This one is a real situation. This is in feet because you should get used to different units. If you're working in imperial like that, like gravity is negative 9.8 meters per second squared, it's 32 feet per second squared. So that's why there's a 16 here. Half of gravity in imperial is 16. It actually works nicer because then you can factor it nicely, like math. That's why part of the reason why I used feet here, because you can do some factoring and we can make it nice whole numbers that it works out to be for when you're first working on this. You have to think carefully about this, right? Something you might not have from physics is like returns to Earth here, or as normal people would say, when it hits the ground, right? I'm going to throw this ball up and then wait for it to return to Earth, right? It's when it returns to Earth, i.e. hits ground, right? If you want to know when it hits the ground, you might need to think first about where its position is what? What's its position? Remember, this is not physics. We might have an initial height here. You should be able to interpret this in terms of what you know from physics, right? There's 3 terms there. This is the effect of gravity. The squared term, the quadratic term is the effect of gravity. The linear term is the effect of your initial velocity. The constant term is your initial position. Without this, it just means you started at 0. With this, it means you started 640 feet off the ground. Hence, from the tall building, right? If you want to know when it hits the ground, find the time when... You first find the time when it's 0, and then look for the velocity. Can you work through some of these questions? You got about 20 minutes now to work through some of these questions. There's lots of questions there. It's going to take us likely today and next time. Today and part of next time it'll